Welcome to the Audioslides for our paper titled In Vivo Characterization of Brain Ultrashort-T2 Components that was recently published in Magnetic Resonance in Medicine, is being featured in their highlights segment. This work was done the majority at UCSF, and I am Peder Larson, and this was done in my group there. And the first author is Tanguy Boukno, who did a bunch of the work on this project while he was a visiting graduate student in my group coming from Paris. So the motivation for this work is to look at what I'm calling the Ultrashort-T2 brain component. This has been demonstrated in ex vivo studies and is likely associated not with the usual water components that we detect in myelinated tissue, but rather with the protons in the myelin membranes themselves, hence the name myelin membrane. And these are bound protons, so they have a very fast relaxation rate. And these offer a different potential than our other water imaging methods in that we're directly measuring the myelin sheaths themselves, so possibly directly measuring their density and structure. And these components are also not seen in typical MRI sequences because of TE limitations. But because of the central role myelin has in the nervous system, this could be interesting in a wide range of diseases such as multiple sclerosis, leukodystrophies, Alzheimer's disease, for looking at brain development. So a brief outline of what we've done in this project, where our goal is to characterize the Ultrashort-T2 component in the human brain, both at 3T and 7T, is a majority of what we'll show is we had to develop some specialized methods to detect and characterize this component. This includes a 3D ultrashort echo time, or UTE, acquisition. We also have to do some multi-frequency reconstructions to correct with off-resonance blurring, and finally apply a multi-component model. So a little bit of background on this Ultrashort-T2 brain component. It started, to my knowledge, the earliest presentations of this in the literature were in the early 2000s and more anecdotal. Then more recently, there's some more detailed ex vivo studies, very nice studies done. And then recently, there's been a bit more interest in this component and doing some nice in vivo studies as well. And I'll go through some more images from each of these in this presentation. So these are the first, to my knowledge, images. And what we can see at the far left here is inversion recovery, or IRUTE, using late TE subtraction to try and highlight only the Ultrashort-T2 component. And you can see this shows a nice signal corresponding with typical white matter anatomy in a normal volunteer, but the same technique, IRUTE with late TE subtraction in multiple sclerosis, does not so much signal at all, as we would expect, because this is a demyelinating disease. I got into this field in graduate school, where I was working on long T2 suppression pulses to improve the contrast in UTE, and saw this similar signal where it did correlate with the white matter when looking at UTE with these long T2 suppression pulses, and there was sub-millisecond T2 star decay rates of this component as well. So this is what was my initial motivation to pursue this project, was now over a decade ago. So in 2011, this fantastic paper came out in MRM, where the group here from Vanderbilt looked at about the myelin extract and several myelinated tissue extracts, where they measured T2s using a spectrometer and found that these survived immersion in deuterated water, or D2O, confirming that these are not due to water within the myelin or from chemically exchangeable protons. And they did a number of nice experiments, and this concluded that these are likely attributed to methylene protons, which are the most common common bound protons expected in myelin. And overall, this pool might be the same size as the water pool in myelin, so the myelin water fraction. Just a year later, this other nice study came out from the group at Penn, where now they also measured similar extracts in tissue samples, and they showed an additional, they actually measured the chemical shift to be what would be expected for methylene protons in these myelin extracts, and a complicated spectrum because it's not simply the methylene group, but this is nice confirmatory that there is a chemical shift, and they also show that there was a strong correlation between myelin content in samples and the amplitude of this resonance, really setting the stage that this could be a very quantitative measure of myelin content. They also took it a step further, did inversion recovery and late echo subtraction to perform long T2 suppression, and showed some nice images here in a rat spinal cord. And so this technique has been applied more extensively in vivo, being led by the group in UC San Diego. And they use the same technique, inversion recovery and echo subtraction, to highlight the Ultrashort-T2 component. And they've shown this consistently in several papers. They also measured this in humans to be T2 star around 300 to 500 microseconds, T1 to be relatively short as well, 225 milliseconds, and the relative proton density to be about 4%, which is a little less than typical myelin water fractions, but still very imageable. More recently, they've shown that this, in a multiple sclerosis, which is a demyelinating disease, that you can see the loss of this Ultrashort-T2 brain component in demyelinated lesions. And some of these correlate nicely with the typical empty rage and flare methodologies. And yellow highlights here several lesions where the visualization was actually improved by using the inversion recovery UTE approach. So in our project, we aim to do this whole brain Ultrashort-T2 star relaxometry to characterize the Ultrashort-T2 component. So this is built around a 3D ultrashort echo time, or UTE pulse sequence. I chose 3D because the half pulses that are required for 2D UTE are very susceptible to gradient and system imperfections. So using a non-selective 3D acquisition, we can get very short echo times and be quite robust. We shift the TEs to perform relaxometry. We also chose to acquire each projection, each radial line for all TEs, and then move on to the next projection in an attempt to minimize motion artifacts. A couple of the other key parameters I'll point out: we acquired a total of 32 echo times and whole brain coverage at 2.2 millimeter isotropic resolution, with undersampling factors between 4 and 6, for which we reconstructed with eSpirit using the Berkeley Advanced Reconstruction Toolbox. And I should also note that this was each one of these data sets with the 32 echo times and whole brain coverage, even with this acceleration factor, took approximately 45 minutes to 1 hour per scan. Now, just as a fun aside, there are some other interesting things you can do with UTE. Here's some fun we had several years ago, imaging a violin, and you can pick up the short T2 components in bone that you would normally not see with conventional imaging, just sort of showing the fun things you can do with UTE MRI. But I digress. Let's get back to the main point of this project here. So one of the first issues we had was we observed these unwanted fluctuations in the TE data. And here I'm showing some data from a water phantom, so very uniform, should be a nice mono-exponential fit. But as we can see, the residual fit error of this mono-exponential fit is very large, and it has this terrible sort of oscillation on it. Especially if we're expecting a chemical shift of the Ultrashort-T2 component, this is going to be a major confounding factor. And we even did an experiment here where we repeated this 4 millisecond echo time several times, and we can see the oscillations in this value. Our hypothesis is this is an eddy current effect. Then we saw even some fluctuating image distortions between the TEs. So what we did to get rid of this was we used a randomized echo time ordering. And this basically removes the coherency. There may still be eddy currents, but at least they're not coherent between projection to projection, because this random ordering is random for each different projection or spoke. And thus we see no coherent artifacts, substantially reduced, and a much better mono-exponential fit in this phantom. Now this has the interesting effect that it really changes the auditory profile of the pulse sequence. So if we listen to a sequential ordering here, we can hear the case-based trajectory looping around here, kind of as this illustration is showing, and sort of the oscillation of changing the projection angle. Right, and it sounds reasonably tonal and interesting. And then if we go to our random ordering, you'll notice quite a different sound. Is that now, because things are random, we've actually sort of created a white noise, very incoherent sound, very atonal, and sometimes I refer to this as the blender pulse sequence, because it really makes it sound like you're inside a blender while you're there. Okay, so we've got our blendered data with our randomized ordering. Then the fitting was actually relatively more straightforward. We apply a multi-component model, includes T2 star, a frequency shift component, also a possible phase shift. One subtlety, but that was very nice, is we fit these to complex valued images. So we're preserving frequency and phase information in all of our data to improve our estimations of the frequency shift. This code is available at this link below on GitHub if you're interested. Okay, so into some results, some data here. So this is data in the same healthy volunteer, both at 3T and 7T, where we've applied both single component, n equals 1, two component, n equals 2, and three component fits. And what you can see most obviously here in the 3T data is this: obviously the single component fit is inadequate. There is a clear Ultrashort-T2 component that's decaying a lot within the first millisecond or so of the data acquisition. And if we go to 7T, you see that the decay is maybe quite a bit faster, maybe within excuse me, half a millisecond or so. And then the top plots and the middle plots here of the normalized signal are the real and imaginary component. And we found these very useful because we can actually see nicely oscillations in these signals that are consistent with there being a frequency shift. And we really wanted to have this confirmation, given that we had seen some oscillatory eddy current artifacts. This real and imaginary fitting was very inspiring to give confidence in these fits. We also found that of these compartment models, the two-compartment model was more appropriate, which was measured by the Akaike's information criteria across the entire brain. This held at both 3T and 7T. So all results I'll show from this point forward are two-compartment fits. Now we ran into one other problem to go from a single voxel fitting into making maps, and that's that if we have this large frequency shift of the Ultrashort-T2 component, there will then be substantial image blurring due to phase accumulation during the 3D radial acquisition. So to address this, we did a multi-frequency reconstruction and fitting strategy, where you can reconstructed both at the water frequency and then also demodulated at approximately the lipid or fat frequency. And then we use the reconstructions at the fat frequency to generate our Ultrashort-T2 component fits. And we use the water frequency reconstructions to generate our fits of our long T2 component fit values. So putting these all together, these are the type of maps we would obtain both at 3T and 7T, and this is in the same volunteer here, of several components. So first, the Ultrashort-T2 fraction here, we now can see with these multi-frequency reconstruction that this corresponds to the primarily the white matter anatomy. This is most obvious at 3T, At 7T, we had a lot more challenges performing the fitting and getting reusable maps. I think this is due to the usual culprits of B0 and B1 inhomogeneity and also possibly blurring artifacts, as I'll discuss later. Another thing we can see in these maps is that the frequency shift of the ultrashort component does not seem to have a much correlation with the anatomy, nor does the T2 star values, these T2 star ones that we're measuring of this component. They're relatively consistent across the brain. And if we look at the distribution across the brain of the Ultrashort-T2 component, so the T2 star value and also the frequency shift at both field strengths, we can zoom in on a couple of our volunteers here, and typically the T2 star values at 3T were around 0.5 to 0.7 milliseconds. At 7T, they're quite a bit shorter, near 200 to 300 microseconds. And then the frequency shift was centered approximately at minus 330 hertz at 3T, minus 900 hertz at 7T. This corresponds to a 3 ppm shift from water. This is very similar to the methylene proton frequency. And you can see in general the distributions are not as clear or as clean at 7T, can likely due to some of the challenges of off-resonance. We look across a few ROIs here. So we've chosen the corpus callosum, which is a highly myelinated region, a mixed white matter region, so it's predominantly white matter, although there may be some gray matter mixed in, and then a mixed gray matter, which is predominantly gray matter, but with some white matter mixed in. And we do see that there was a significantly larger Ultrashort-T2 component fraction in the white matter voxels as compared to the gray matter. And there were no significant differences in the T2 star or the frequency offset values between these different ROIs. So some of the limitations and challenges of this study, first is that it was really crucial that we had this specialized approach. We tried a naive approach and we needed the randomized ordering to reduce eddy currents. We need some sort of way of handling the off-resonance, the blurring that comes with that. And then we highly leveraged parallel imaging in this study. Overall, the fitting is challenging because relaxation rates are quite a bit faster than the rate at which off-resonance is accumulating. So there's almost not enough time to visualize the off-resonance with such a high relaxation rate, but I think we've shown that definitively in this study. Then we have always with UTE and short T2 star, you have to be aware of blurring artifacts due to T2 star decay. And 7T was going to suffer the most from this because the T2 star was shorter than the readout duration, so possibly limiting the quality of our 7T maps, and just the susceptibility near the sinuses here led to some very poor fits. Overall, the fact that there's such a shorter T2 star at 7T, this may negate any polarization gain we might expect by going to 7T. In comparison to prior work, we measured slightly longer T2 stars than some prior work, and a possible explanation is that T2 star, if you assume no off-resonance frequency shift, will give you a shorter value than if you actually incorporate the off-resonance shift when you're measuring T2 star. So that's our best explanation as to why we may be measuring slightly longer T2 stars. And the fact that T2 star shortened at higher field agrees with the ex vivo studies, which were performed at higher field. And there's also additional possible T2 star shortening because you're using extracts that went in the fixing or extraction process could have a shorter T2 star as well. So in conclusion, we believe these are the first human brain measurements that demonstrate the chemical shift of the Ultrashort-T2 component. So again, further providing strong evidence that we're measuring methylene protons in the myelin phospholipid membranes. And we characterized this showing that we had larger fractions of the Ultrashort-T2 component in white matter, have typical T2 star values here, and frequency shifts. It's about -3 ppm. Really, this is all enabled by the specialized Ultrashort-T2 star relaxometry methods that I covered. And overall, the T2 star value, particularly at 3T, and the concentration and amplitude of the signal are very reasonable for performing in vivo imaging. So I think these characterizations will enable the design of future pulse sequences and methods to image this component, and also enable this further investigation in disease states to see how both the Ultrashort-T2 fractions as well as maybe T2 star and the frequency shift may change in certain demyelinating diseases. So thanks for listening to these audio slides, and here are all the people, my group, my collaborators, the funding sources: NIH, National MS Society, GE Healthcare, and UCSF. And I'd also invite you to check out these web pages to find more resources about this project, as well as code repositories if you would like to implement some of these techniques yourself. Thank you for listening.